All right, hi everyone. So today we are going to be talking about gas density and molar mass. So I was going to show this video in class just about density in general, but I will post it on Canvas. It's a fun video to watch, just about like a folk tale about Archimedes and kind of how he used the idea of density in order to find whether or not the king's crown was actually made of gold. So again, I'll post it on Canvas. It's a very fun video, but if you forgot what the equation for density is, or you don't really remember exactly what density is, I highly recommend watching it. So density is basically just how closely packed the stuff is in an object. And a way that we can just give like the basic definition of density in terms of chemistry is mass per unit volume. So the equation for density is mass divided by volume. Here's kind of a picture of what's going on here. Something that has a very high density will have a lot of mass within that volume. And then medium and low density have less and less mass as we get to low density. Gases, of course, are very low density because there's a lot of space between the particles in a gas. Now, molar mass, just a little bit of review here. It's the mass in grams of 1 mole of a substance, and the units are grams per mole. Remember, we use these, and we get these numbers from the periodic table, and we use these when we're converting grams of a substance to moles of a substance or moles of a substance to grams of a substance. So when we're using our ideal gas law, that PV equals nRT, remember N in this equation is number of moles. So sometimes we might be given mass, or if we're given, say, the density of a gas, and we know that density has the mass in that equation, and then we have the ideal gas law with moles, we're also going to need molar mass to relate those two things together, which I'm going to derive the equation that we're going to be using for you guys in a second, so you'll see what I mean in a second. But remember, like I said, when we were using stoichiometry, we were converting mass to moles and moles to mass using our molar mass. Now I'm going to use a new notation here where mass, lowercase m, and moles, lowercase n, those are not new, but now I'm going to call molar mass, so this is the number that we get from the periodic table, I'm going to call that uppercase M, all right, or capital M. And that way we can use this in equations. Now, remember from stoichiometry, if we were given, say, like the moles of a certain substance in order to convert, if we were given the mass of a certain substance in order to convert to moles here, I would be dividing by the molar mass. Okay. So remember, if I'm given mass in grams right here, I would then use my conversion factor. So I'd put my multiplication symbol right here, my line for my conversion factor. And then on the bottom, this would be the number from the periodic table, our molar mass under 1 mole. And then I would get moles here. Now, if we use our notation in that third bullet point above, the lowercase m, lowercase n, and then uppercase m, I get m times 1 over big M, which is our molar mass, equals n. Now, of course, little m times 1 over big M is just little m over big M, and that's going to equal n, our number of moles. And then I'm just going to rearrange this equation here to get an equation for my molar mass in terms of m, our mass, and n, our number of moles. All right. So this is a new equation that I'm going to use in order to derive the new equation that I'm teaching you guys today. So what we're going to do here in order to derive this equation is I'm going to start with the density equation. So remember, my density equation is density equals mass divided by volume. And then from the last slide, our molar mass of a substance is going to be the mass divided by moles. And then what I'm going to do here is I'm just going to solve this equation for mass, which I'm just going to multiply both sides by number of moles, and I get mass is equal to molar mass times number of moles. Now I'm going to take this equation and I'm going to plug it into my density equation. All right. So now next step is I'm plugging this in for M in my density equation. And then I get density is equal to molar mass times number of moles divided by volume. Next step here, I'm just going to solve this equation for volume. And I get volume is equal to molar mass times number of moles divided by density. You guys don't have to know all these steps, okay? I'm just showing you how I get to this last equation here. Not this one, it's actually on the next slide. So again, I have volume equals molar mass times number of moles divided by density. And then we also know from the ideal gas law that pressure times volume equals N, which is our number of moles, times R, which is our gas constant, times temperature. And then I'm going to plug my volume equation that I just derived into the volume equation in the ideal gas law. So I end up getting pressure times the volume equation that I derived, which is molar mass times number of moles divided by density, equals number of moles times R times temperature. So now we can see that I have N number of moles on either side of this equation. So I can cancel that out by just dividing both sides by N. So those cancel out. And then just kind of rearranging this right here, I get pressure times molar mass divided by density equals R, my constant, times temperature. Now what I'm going to do here is I'm just going to solve for my molar mass, just to get an equation that kind of looks nicer and is easier to remember. And so I'm going to multiply both sides by density and divide by pressure in order to solve for big M, molar mass. And I get molar mass M is equal to density times universal gas constant R times temperature times pressure. Sorry, divided by pressure. You guys can see it on the screen. So a good way to remember this equation, it's very silly, but we say M equals dirty P because DRT is like dirty over P. I know, it's silly. But again, remember you have a 3x5 note card to write this equation on to use on the test as well. Now again, remember our big M is our molar mass in grams per mole. D is the density in grams per liter. R is our universal gas constant, which is 0.0821 liters times atmospheres over moles times Kelvin. T is our temperature in Kelvin, and then P is our pressure in atmospheres. All of these units have to be in those units that I've listed, again, because we're using 0.0821 as our R. Constant here. So in order for the units to work out, you have to have your pressure in atmospheres, you have to have your temperature in Kelvin, you have to have your density in grams per liter, and of course molar mass is always in grams per mole. So here's just my writing all on one page about how to solve this or how to derive this equation that you just learned. All right, let's do an example. So we have determined the density of chlorine gas at 3 atmospheres and negative 30 degrees Celsius. So we have some givens here. I'm giving you that the pressure is 3 atmospheres and that the temperature is a negative 30 degrees Celsius. Of course, we don't want Celsius, we want Kelvin. So I'm going to add 273 to this and I end up getting 243 Kelvin. Now I know that this is chlorine gas. So remember, chlorine is a Brinkelhoff element, a diatomic element. So that means it's going to be Cl2. And from this, I can get that the molar mass of chlorine from the periodic table is 2 times 34.54 grams per mole. So the molar mass of chlorine gas is 70.9 grams per mole. So I also know that the universal gas constant R is 0.0821 liters times atmospheres divided by moles times Kelvin. Now I know from that equation that I derived that the molar mass M is equal to density times R times T, temperature over pressure. And so I just want my density of chlorine gas, and I have all of the other variables. So I'm just going to solve this equation for density. I multiplied both sides by pressure, and then I divided by R times T in order to get density there. Of course, you don't have to derive the equation algebraically. You can just plug in your numbers and solve for D. That would be fine as well. And then plugging in my numbers here, remember big M molar mass is 70.9, pressure is 3 atmospheres, R is my constant 0.0821, and then my temperature is 243 Kelvin. So plugging in these numbers into my calculator, we can also see how the units work out here. Moles is on the denominator in that molar mass there. So that is going to cancel out with the moles on the denominator in the denominator. And then we have atmospheres canceling out with atmospheres and Kelvin canceling out with Kelvin, again, because the Kelvin in the universal gas constant is on the denominator of that unit. So we end up getting grams per liter. You can see grams is right here in that molar mass number, and then liters is on the bottom here in the universal gas constant R. So grams per liter for my density unit. And we end up getting 10.7 grams per liter. And that's our answer. Okay. Next example, we have determined the molar mass of a gas when 8.67 grams of it occupies 12.2 liters at 90 degrees Celsius and 0.53 atmospheres. So here we have some givens. I know that the mass of this gas is 8.67 grams. I know that the volume is 12.2 liters. I know that the temperature is 90 degrees Celsius, but of course I don't want Celsius, I want Kelvin, so I'm going to add 273 to this. And then I know that my pressure is 0.53 atmospheres. Now, of course, we also know that our universal gas constant R is 0.0821, and I want to know the molar mass, big M. So I put M equals question mark. Now, if you remember, again, our equation that we derived today is big M, molar mass, is equal to density D times R, my constant, times temperature divided by pressure. So I can see that in order to get my molar mass here, which is what I want in this problem, I need my density because I know R, I know temperature, I know pressure. So all I need is density here. Now, if you recall, density is equal to mass divided by volume. I'm given a mass and I'm given a volume. So I can find density first and then I can plug it into this equation. So I get density is equal to the mass, 8.67 grams, divided by the volume, which is 12.2 liters, and I end up getting 0.71 grams per liter here. And then now that I have the density, I can plug it back into my M equals dirty P equation. So I get big M equals the density, which is 0.71 grams per liter, times R, 0.0821 times my temperature, which is 363 Kelvin here, divided by the pressure, which is 0.53 atmospheres. So we end up getting that molar mass is equal to 39.9 grams per mole. If we look at the periodic table on here, we can see that argon has a molar mass of 39.948 grams per mole. So this is probably argon gas. Here. And I think that's it. Yeah. Okay. So that's my last example. So we derived a new equation today that has to do with the density of gases and the molar mass of those gases. And then we did a couple examples. Remember, we are relating a few different equations here. So in this example here, we had to use both the molar mass equation that I taught you today and the density equation. We maybe would need the ideal gas law equation, so these are all equations that you can use. Keep them in your back pocket in your arsenal, and you can use them in these problems. Remember, write down your givens first, and then write down your equation, plug in your numbers, and solve. Let me know if you have any questions, and good luck.